Okay, now this is Sabine Hassenfelder. She's talking about special relativity. This is why you misunderstand it. Now listen to what she has to say. We all live basically in different time zones, but this, whatever time is for you, is the same time it is here, only you just designate it as a different time because that's where you live, is in a different, the sun comes up at a different time for you. That's all it is. Now listen to what she says.
An hour might feel longer if it's a job interview, but even the most awkward conversation doesn't actually slow down time. And yet, Einstein said, time can slow down. It doesn't always pass at the same rate.
Now, that's an interesting statement. Okay, basically what Einstein is saying, that velocity determines time. It doesn't. You can go fast and still be going at the same time when you hit where you are as the guy standing and not moving at all. It's just time is time. It doesn't speed up because you speed up. It doesn't slow down because you speed up. It doesn't do anything other than tick by. That's all it does. This is kind of nonsense, to be honest with you. They're showing, oh, he's stretching time out. No, he's not. He's just going faster. Okay, my friends, so Einstein says that time can speed up and slow down. Well, what are they saying at Fermilab? This is Kirsty Duffy, and she's talking about neutrinos from the Big Bang. And one of the questions that puzzled people since the beginning of time is, well, how did time start? Where did it come from? Where did God come from if there's a God? They say there's no God, there's a Big Bang. And that's what I take from this. I could be wrong. Let's see what she has to say.
One of the questions that has puzzled people since the beginning of time is, well, the beginning of time. We're pretty sure the universe started with what's known as the Big Bang, but much of our evidence for what happened in the early universe actually comes from information hundreds of thousands of years later. How do we measure the Big Bang? And how could our favourite friends, neutrinos, revolutionise our understanding of the early universe? That's what we're talking about today on Even Bananas.
Now, I'm going to show you what neutrinos are in a second. And she's a neutrino physicist, and so is Don Lincoln from Fermilab. And here's what she has to say about neutrinos.
When you think about the Big Bang, your first thought might not be neutrinos, but it is if you're a neutrino physicist. The Big Bang should have created equal amounts of matter and antimatter, which annihilate if they come into contact.
Now, these are all assumptions that they could be based on something, but they're really based on nothing, to be honest with you. And as far as I can see, they don't understand what a neutrino is. Let me show you what neutrinos are, and then we'll come back to Kirsty. Okay, so let's see what a neutrino is. And this is from Fermilab. These are muon neutrinos, and these are electron neutrinos. The two of them together make what's called a Dirac neutrino. They can separate, and the muon black ball part can go on its own and never changes. The white part turns into a shower. And here they are right here. We did this, Rod Warren and I experimented with light, and were able to separate well, Rod did this, really, to be perfectly honest with you. I saw what he did and I was just blown away. So I got in contact with him, and we spent 5-6 years working on this, and he got it down to where he could separate the black from the white, and it was very simple. We saw the different speeds of the red versus the green versus the blue. We could see light speeding up. We could see light slowing down. I know we're not in a vacuum, but space is not a vacuum. Space is completely saturated with these particles. They are nothing but light particles. They come from the sun. Now, some of them come as strictly muons. Some of them must come as strictly white. I can't see how that's, if the muon and the electron showers were together as neutrinos, and the muon went off on its own, well, the white had to go somewhere on its own, and we could see that. We could see them totally separated coming back, totally separated at the input to the Venturi. The Venturi crushed everything. The fields is what you're dealing with here. The fields crush, and you get this huge spray of white particles, and the black just goes on its way. These are neutrinos. We showed them. Okay, Fermilab is guessing what happened 13.8 billion years ago. And here's what she has to say. We already know all this stuff. Well, they don't know. Not a single word she's saying they know. Listen.
Redshift. To understand cosmological redshift, we need two key ingredients. The expansion of the universe.
Which is, who's saying the universe is expanding? What they're looking at is light slowing down. And they think it's because everything's moving away. No, light is just slowing down because there is nothing but a particle zoo in front of the light, so it's concussing. I showed you this. Now they're talking about wave-particle duality.
And wave-particle duality. First, we know that the universe is expanding.
No, we don't. Nobody can say that. Not a single person can say that.
Which means that space-time itself is stretching out.
No, it isn't. Space-time is just the time it is wherever you are when you're there. Somebody else is in somewhere else at that same time. It doesn't mean that they're stretched out over there.
Second, wave-particle duality tells us that we can think of a neutrino as a wave just as much as a particle.
It's a particle, and in front of it is a wave of magnetic influence. There's a particle's back here. I showed you the particle.
Our previous video introduced wave packets, which look something like this. As space-time expands, the wave packet stretches out, like a piece of string pulled tight.
That's just the most ridiculous assumption. It really is. I have a hard time dealing with this. When light comes through anywhere, it slows down when it interacts with everything that's in front of it. It's just there's nothing it can do. Its field pushes and bounces against all that stuff, and it boom, 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 and it slows down. Light only goes a certain distance, doesn't go forever. Not in the atmosphere that we're in, and even in the space, it collects out there as it bumps into each other. They're collecting, the dark matter is collecting, and it may collect in certain areas where there's nothing but dark matter. In other places, there's nothing but the muon neutrino part, the electron neutrino part, and nothing but that white shower. We know they can separate. Nobody knows anything about this yet. Not a single person. And I just sent off to the Department of Energy because they're spending millions and millions and millions of dollars, billions really, and probably trillions in the last certain number of years to look into this. Not a single thing has happened other than walking around in circles saying, don't look at what Roger's showing. Roger, he's nobody. Well, that's the problem. They think they're full of it themselves, and they are full of it. All right, you see this? This is how light slows down. Here's where it's coming in really fast. The waves are right next to it. And by out here, you got this black wave between each wave. It's nothing but push to shove. You push me, I shove back. You push me, I shove. Sooner or later, I can't push you hard enough to get you out of the way like I could back here. I don't have the energy anymore. I've used up all my energy until I got to here. That's the blue light expanding. This is through glass, I'm pretty sure. And again, this was Rod Warren. Absolutely fabulous work. And see, here's the blue again, coming in. And it started to split up out here. So we can see it's two particles. Back here, you can't even tell what it is. It's just one single looking particle. Well, here we can see that it is the two particles, just like a photon. We have a real hard time seeing the blue. It's just too powerful, too fast. Much faster than the green and the red. Absolutely, incredibly much faster. Now, here's another one by Rod. We can hardly see the Higgs fields. They're just a little bit strong. We can, however, see that we separated from here. There is no black. There's none over here. You see it over here? It's saturated with black. You see all the black? You see over there? Nothing. No black whatsoever. And what it is, it's an off-center Venturi. So it's hitting here, just pushing all the black stuff, which is the hard bangers. The white ones, they can just go any way they want. They just, pew! So they come through here, only white. Here, the bangers go that way. All right, this is light from a red pulsed laser. There is a particle in here, which I showed you before, the black and white particle, and its field is what causes the wave. The particle is inside the wave. So the wave has to come through all of these particles, which are nothing more than gaseous particles and light and everything else. It's completely saturated, but this is here on Earth. In space, what do you think is there? Take a second and think about it. How does the light come from the sun to us? This is it right here. It concusses with solar panels and creates electricity. It's not nothing. It's a saturated universe we live in. And Don Lincoln from Fermilab agrees with that. He says it's a quantum foam. And we have shown this. Okay, a lot of people don't realize, but you can go to Yale all through quantum mechanics free. You don't get any credit for it, but at least you can go there and see what they're saying. I went and I found out they didn't know what they're talking about, and he admits it. Listen.
So this is a very exciting day for me, because today we're going to start quantum mechanics, and that's all we'll do till the end of the term. Now, I got bad news and good news. The bad news is that it's a subject that's kind of hard to follow intuitively, and the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense the pressure is off for you guys, because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. Right now, I am the only one who doesn't understand quantum mechanics. In about 7 days, all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else.
What can I say? All right, I have a college education from when I first, after I got out of the Army, they gave me a free education, so I went and I used up my GI benefits. But all I did was learn, you know, I learned stuff. I'm not saying I didn't learn anything, but I'll tell you, since then, what I learned now negates everything they taught me. I use Coursera now. They're free. It's unfortunate they're not making any money, but they're free, and you can go to any school, almost any school there is. I've gone to the University of Geneva in Switzerland, online, of course. I've gone to Johns Hopkins, Rice University, well, all kinds of them. Because you don't even have to ever interact with anybody. You just go and see what they say. It's just like the one I just showed you from Yale. You go there all day long and look at their courses. But that's it. You don't get anything for it. If you're looking for a piece of paper, you're out of luck. I wasn't looking for that. I was looking for what do they have to say, and I realized I had more to say than they did. And my stuff was right. I just showed you light moving forward. This is light accelerating. If you can't see acceleration there, I don't know what to make of your thought process. This is accelerating, just like a jet fighter accelerates through the speed of sound and has that concussion wave. Here we came into a Venturi, which forces acceleration. However, in addition, we made the Venturi so tight that the black couldn't get through only the white. And these are what they call interference patterns, but they're not interference. They are pushing patterns. They're push to shove. These are field patterns. Get away from me, you get away from me. No problem. Stay in your line, I'll stay in my line. That's what's going on here. It has nothing to do with overlapping waves. This is a single slit. So these neutrino specialists should be paying attention to what's obvious. And I've been showing this for many years to Don Lincoln at Fermilab, and I've been shut off. I can't comment there anymore. And same thing with Kirsty Duffy. They have their own little piece of the pie, and nobody else can take a bite. This is the green. Same thing, same photons. It's just that they have a much more powerful impact. And I believe it's due to the spinning. Okay, they're looking for neutrinos. These are neutrinos. They change flavors, they say. In other words, they change their impact value as they move forward because they're impacting more and more and getting either less intense or more intense. We put them through a Venturi, causing them to get more intense, turning into photons and then into muon and electron neutrinos. And that's the only way you can do this is with an accelerator. Now they use an accelerator spinning around miles and miles and miles and then hitting these protons head on. And instead of seeing these particles, they see absolute garbage, just nothing but trash. And then they pick through it to see if they can find these, and they do. But they still have no idea how they really originated. All they see them is particles. Truth be told, all they can do is see these particles in a big shower. So they see these, and then they see these. This is in the transition state of neutrinos turning into photons, as I will show you. Okay, you saw the Dirac, you saw the Majorna, you saw the electron neutrino, the muon neutrino, it's all right here. They change flavors, they change values as they move forward. These are, I don't know what, but they're light every one of these is a particle of light. This is the photon, which is directly in line with the Venturi. That's why it's so pronounced. These are just sort of light particles moving forward, but once they approach this interactive state, look what happens to them. Look at this. Unbelievable. Back here they were just little bitty things. Look at this. Bzzz. That's just before they explode. And then they turn into black and white separated. You see that? This is the green. Absolutely identical to the red, only much more combustive. And this is the green electrons in the trail. These are the electron neutrinos. And then you show up with the photons. It's not hard to see. Light spins. That's how it travels. It doesn't travel in one straight line. It spins all the way through. That's why the Venturi is here. Some of it is going that way, some of it's coming over the top and going this way. That's what creates the interference patterns on both sides. Each one of them is a spinning line of particles. Okay, keep your eye on this. These are what they call Higgs fields. This is just the white portion, which is the electron shower neutrinos. They're looking for black particles to get back together with. And here's when it happens. They recombine with the black particles and turn into Higgs fields. It's not the other way around where the Higgs fields create matter. This is what creates the Higgs fields, and they turn back into matter. Now let me show you what CERN sees for Higgs fields. That's what they see. They're hitting huge things head on, just getting debris. That's all they're looking at is trash. The first particles they see are the red. The red are the weak ones. They're staying nice and tight right around a collision because they're just weak. They can't go flying. But the red and the green and the blue and the yellow and all those, they take off and they never come back. That's why we see so much red in these huge fields of Higgs fields, and that's what they see. It's the exact same thing. The only thing is we're using photons, so we can see them precisely. They're just looking at debris. You see this? This was some work done by Fabien Boulez. He put through the red and the green at the same time through the same Venturi. All it is straight up like this. He had the red going through the bottom, the green going through the top. You see the green reconcussing way out here. The red's done. Case closed for the red. Get out of the way, I'm coming through. You can see the same particles. And you can see a little bit of the red, just a little, barely the red is out there. And it's getting intermingled with the green. It's just a collision of particles. One of them's just faster than the other one, that's all. I'm spinning much faster than that one. This is exactly what Don Lincoln from Fermilab says. This is his diagram. It shows a black particle he says it's a fixed particle, never changes. Then he has the point particle, which he says there's nothing there. There has to be something for a field to surround it. And here's what they are right here. Those two are these two. And then there's another two of them. This is basically an electron. They call it a gluon, or a Dirac neutrino, same thing. There's so many names now, it gets very confusing. As this is coming through the air, this one is getting glowy. See how it's glowing? These little white particles, you may not be able to see those. But those little white particles right there are why this is glowing, because it's coming through the air concussing with them. All right, I think you can see those quite well. This one's not concussing. It's just waiting to be able, because it's getting ready to flip. Once this gets all charged up, It flips around the back, this one comes to the front and charges up. That's what the muon wobble is all about. I think I've shown as much as you need to see about electron neutrinos, muon neutrinos, gluons, photons. It's all right there. And it works exactly the way Fermilab says. That one there is the concussor. This one here is just the carrier of this one. This one glows and gets smaller and bigger and burns and all of that. And it burns like hell. And that one just knocks things down. I'll show you again. Okay, this is from Atom Central. They're looking to see what happens to houses and so forth in atomic bomb blasts. And you'll watch. Well, the first thing that's going to happen is the house is just going to combust. And then it just gets blown away. The first particles are going to hit are the ones that are surrounding the black matter. They hit first, then the black matter comes and hits second. Here it goes. All right, the first thing you see is a brilliant flash, which is when the bomb goes off. That's all you see. Now, what do you see in there? Nothing's moving. It's just combusting. Not a single thing is moving. All the wires are burning up and everything. And then, boom, here comes the black particles. I don't think you have to see much more than that. The only other thing I can show you is that the first part was burning. The second part is just concussion. The third part is they come back to go back to where they came from because there's nothing left on the tarmac. It turns around and it all comes back. I think that's pretty conclusive.